section talks all about combinations of functions. And so when we say combinations, we mean to create new function machines by taking two existing function machines and either adding, subtracting, multiplying, or dividing them. Or later, we're going to see what it's going to take for a function to be a composite function of two. Okay, so we're going to go ahead and start off with these simple operation functions here. And so typically, again, it's the notation that I feel like oftentimes gets in the way of the whole idea here. So the names of these functions, of course, sum function of f and g. We also have your difference function and your product function and your quotient function. Okay, and so again, the names for these are a little bit confusing, or at least are oftentimes confusing for some. But the idea here is, again, that we have the function name. If I wanted to do h of x, I'd put the h there, and then of x, I'd put x there. So it's just kind of unfortunate that we use these naming conventions for all three of these, or four of these functions, I should say. But I guess it is kind of advantageous because it does demonstrate the operation that you are doing between your functions g and f, right? And so the definitions are here for these, and they're straightforward definitions, so we're just going to add together the function outputs, or subtract them, or multiply them, or divide them here. So in this next example here, example 1, f of x is the function machine that takes your input and triples it, and then adds 2, and then g of x is your function machine that takes your input and then takes away 5, and then gives you your input, or sorry, your output. And so in this example, we just want to go through and calculate what each of these functions would be. So in this first case, in the case of f of g, we would need to go ahead and, by definition, take the function output for f and add it to the function output for g. Okay? So the function output for f, of course, we're just going to go ahead and substitute that in. That's going to be 3 times the input plus 2. And then to that, we're going to add the output of g, which, of course, is your input minus 5. And then here we just see that we have a couple of algebraic expressions, and we are just going to go ahead and add them by combining like terms. So 3x plus x is going to make 4x, and then a positive 2 minus 5 is going to make a negative 3. So this function is the function that will go ahead and take your input and multiply it by 4, and then take away 3, we find. Okay. For the next one, we're going to go ahead and do the difference function between f and g. So that would be taking the function outputs here and subtracting them, of course. And I would really love to be able to write on my tablet, but as always, you guessed it, good old OneNote. Okay. So can I erase? There we go. Okay. The output of f minus the output of g. And just a note here, right? We are going to do the exact same thing that we just did for the previous example, but instead of adding, we're going to subtract. And keep in mind that subtraction has a minus sign, and that is going to have to be something that we're a little bit careful about, because that is going to change the sign of a couple of our numbers here. So as long as we go ahead and set this up using a set of parentheses, just like I did when I did the sum, then that is going to prevent mistakes, because again, that's going to mean that we signify to ourselves that we're going to have to go ahead and distribute this negative on through to both terms inside this set of parentheses here, and then we'll go ahead and continue to combine, right? So when you do that correctly, you should be ending up here with 2x plus 7. There we go. For our product function, we are going to go ahead and simply now just take the function output for f, which my OneNote doesn't really like to change colors there, so let's go ahead and fix that. So the output of f times the output of g, we're going to go ahead and set that up here for ourselves. So 3x plus 2 times x minus 5. And here, taking a binomial times a binomial, this would have to be something that when we multiply these out, we would have to FOIL this out, or double distribute, depending on what you learned. I'm not going to go ahead and show the work for that. I'm just going to go ahead and write the result that you would get after doing that process. But this is what we should get right here, right? So 3x squared minus 13x minus 10, and then, of course, remembering that that was something that you FOIL out. And then finally, for the division here, this is oftentimes the easiest one, but we do need to be a little bit careful, because whenever we set this up, right, that's going to be the output of f divided by the output of g. That is simply going to look like the following. It is going to look like here, if I fix what I wrote there previously, there we go. That is going to look like the output of f, which is, of course, 3x plus 2, over the output of g, which is x minus 5, okay? Now, the reason that it asks us for the domain here is because, remember that this is one of those situations that we were on the lookout for whenever we were trying to find domains, right? When we have a denominator, we just have to simply set it not equal to 0, and then we would solve that, right? So x is not allowed to be positive 5, and so if it asks us for the domain here, I might go ahead and stick with a capital script letter D there of f of g, or not f of g, that's later. We want the quotient function, f divided by g, there we go, and that is what? Well, that is going to be the interval from negative infinity all the way until we reach 5, and we will unite that with the open interval from 5 all the way to positive infinity. So just being a little bit careful here whenever we are setting up that quotient function, okay? In example 2, it's going to be the exact same type of problem, except they're going to give us two different functions for f and g. And here, instead of actually figuring these out for any generic x, what we need to do is figure out the outputs for these specific inputs right here. So for 1, 5, 3, and 0. So setting these up, f plus g of 1, of course, we're going to have the output of f when we input 1, plus the output from g when we input 1. Okay, I'm not going to go ahead and demonstrate what we get whenever we take these values and substitute them in, just for the sake of time in the video. But what I'm doing here is I'm going ahead and I'm taking my f machine, which of course this is the machine that squares what you give it, and then add 6. I'm going to go ahead and throw a 1 into there and get the output, right? Same thing with g. I'm going to go ahead and plug my 1 into this machine that doubles whatever I give it and then takes away 4. So as for the output of f when you input a 1, that is going to give you 7. And as for the output of g when you input 1, that is going to give you a negative 2. And so if we have 7 plus negative 2, of course, that's going to go ahead and give us a positive 5 here. So when you have an input that is a value we know, like 1, we should expect an output that is a value that we know, like 5. Okay? So moving right along here, we're doing the difference now, evaluated at 5. So the output of f minus the output of g, evaluated at 5. Okay, so again, going through here, for the output of f, you should be getting 31. For the output of g, you should be getting 6. And so 31 minus 6, that's simply going to give you 25. Very, very simple to do. Okay? For the product function, f of 3 times g of 3. Okay, when you input a 3 into your f machine, you should be getting 15. When you input 3 into your g machine, you should be getting 2. So simply 15 times 2, and that, of course, is going to give us 30 for our output. And then finally for the division, again, even though we are inputting 0 into our quotient function, we just need to check to make sure that the whole denominator doesn't end up being 0. And we'll go ahead and figure it out this way, right? So the output of f when we input 0 divided by the output of g when we input in 0. Okay? So if you were to do that correctly for the output of f when you input 0, that should be a 6. And for the output of g when you input in 0 is going to be negative 4. So that's a positive 6 divided by negative. It's going to make the whole number negative, and 6 over 4, of course, reduces to 3/2. Okay? So whenever I give you two functions, the ability to go ahead and set these combinations of functions, the sum, the difference, the product, and the quotient functions, very, very important to do. Another combination of functions that we typically see is what you call a composition of functions, okay? And so the idea here being that if I have two function machines, say g and f, maybe I have this machine g that turns spheres into cubes. Remember how this typically goes, right? Whatever the input is, so the input into g, okay, we typically call that x, and then what we get as the output is simply something that we typically write as g of x. And of course, that is the output from g, okay? The idea with a composition of functions is I'm going to take that output from g and I'm going to go ahead and throw that right into my f machine, okay? And so the output from g happens to be the input into your function f. And then whatever you get out of f, typically this is something that we go ahead and write as f of the input, f of whatever, and what we input here is, of course, g of x. And so we're going to go ahead and write that as f of g of x, and that, of course, is the output from f. Okay? And so what we're going to do here is we're going to construct an entire machine around that process, around giving x to the g machine, getting the output g of x, and then taking that g of x and plugging that right into my f machine and getting the output there. Okay? And so what we're going to do is we're going to give that some special notation. You guys can see that process is in the background because the shell we kind of encased our machine here in is a little transparent. And you see that we have this special symbol. So this is just a circle symbol. What this is this is read as f of g. Okay? So f of g how that's read, or you could also read that as f composed with g. But the idea here is the same. We're still going to go ahead and give this machine an x as an input, but then what we get out is simply going to be f of g of x. Okay? And so by this process, what I want you to notice here is that f of g of x over here, the output from this machine, is simply just going to be what we ended up with over here, which is f of g of x. So if I put all of this together, then what we're going to have is basically this definition right here. A composition of functions, f of g of x, is going to be what I get whenever I take my output from g and I throw it in as the input to f. Okay, and so just a couple of things about what you're seeing here. This is not pronounced fog, even though the circular symbol there looks like an O. This is not f times g, okay? We're not multiplying here. We're taking the output of g and we're putting it into f, and a couple of different things here, right? So turns out that if you were to try to go in both directions of your composition, take the output from g and throw it into f versus take the output of f and throw it into g, it turns out that in general, depending on what g and f are, these are not always going to be the same thing. Okay, you might suspect that they are, but it turns out that this only happens in special cases where we have specific functions f and g that will work that way for us. And then finally, talking about the domain of the composite function f of g, it says right here it is the set of all x in the domain of g such that g of x is in the domain of f. And that makes sense, right? Because in order for us go ahead and even do this process, we have to first confirm that g of x is something that we are allowed to give the f machine first in the first place, right? So we're going to have to check to make sure that g of x, whatever it is, satisfies the domain of f before we're able to call it good, right? So let's go ahead and take a look at a couple of examples of that here. So example 3, we have these two machines. We have f of x and g of x. F is the machine that takes your input and subtracts 4. G is your machine that just simply squares whatever you give to it, okay? So our objective here is simple. We just need to go ahead and find all three of these compositions. So f composed with g, g composed with f, and then g composed with g, right? So we're going to talk about what that means later here. But let's go ahead and start off here with f composed with g. I'll do this in blue, okay? Or try to do this in blue, assuming OneNote will let me. There we go. Okay, so f of g of x, what does that look like? Well, definition, f of g of x is just simply what I get when I take my f machine and I input something. What is that something? Well, that was the output of g. Okay, so I'm going to go ahead and stick with this convention here of doing this highlighting just so we don't lose what it is we're trying to keep track of, right? So I'm going to try to keep track of g of x here. So in place of g of x, what I'll go ahead and do, I think the simplest way to do this is just to go ahead and substitute g of x with what the function output is actually equal to, okay? And in this case, that's simply just going to be x squared, okay? So now that we've gotten, that's us kind of getting the output out of our g machine, and let's go ahead and throw that into my f machine, right? So my f machine, of course, is the machine that goes ahead and takes whatever you gave it and then simply takes away a 4. What did we give it? We gave it x squared, of course. Okay, and so as we kind of take a look at what we've got here, this would be the step where we would need to go ahead and simplify as much as possible. I don't think that there's any need for those parentheses there any longer or the highlighting, so I'm just going to go ahead and write out the final result here of x squared minus 4. Okay, so very simply done. Let's go ahead and do this next one here in yellow. So now we're going to go ahead and reverse the direction of the composition here. And so we're now going to go ahead and do g of f of x. So g composed with f of x is by definition equal to, take your g machine and throw in something. What are we throwing in? We're throwing in the output of f, okay? So we'll just keep track of the output of f as we go through here, right? So the output of f, of course, that's the machine that takes whatever you give it and takes away 4. Okay, so we're going to go ahead and substitute that in for f of x into my work here. And then finally, we go ahead and plug into the g machine and follow along with what the g machine does, right? So your g function is simply the function that takes whatever you give it and squares whatever you give it. And what do we give it? We gave it x minus 4, okay? And so x minus 4 is the binomial that we are going to go ahead and throw into this g machine, and that means that that's going to be squared, okay? Now, I don't want you to leave it like that. That's the factored form. I would like you to go ahead and expand this, and I'm not going to go ahead and demonstrate how that's done. You can go ahead and look to a previous video for that. This could be something that you FOIL out or use one of your special product formulas for, but I will tell you that what you will end up with here is x squared minus 8x plus 16 as the recipe for how to get the output given the input for g of f. And then finally, this last case, this might be something that might have you scratching your head a little bit, but what this is, again, is you are calculating g of x. And so if you kind of interpret it in terms of the machines that we had before, we're plugging something into my G machine. What are we plugging in? We're plugging in the output from G. So basically what this is going to be is we're going to loop this around twice. We're going to plug in an X. We're going to get it out of our G machine and call that G of X. And then we're going to take that G of X and loop it all the way back around into the same machine and get G of X. Okay? So we're going to keep track of G of X here. So this is the machine, of course, that squares whatever you give it, so I'm going to substitute that in. So g of x squared, and of course g is, again, the machine that squares whatever you give it, so we're just going to go ahead and square what we gave it. What did we give it? We gave it x squared. Okay, so we're going to go ahead and square an x squared, and just remember, according to your exponent rules, that is simply going to be x to the fourth. Okay? So there we go. So 3 different function compositions there. Again, just kind of developing this way of making sense out of how to get these function formulas and that kind of thing. So let me know if you have any questions over that. Example 4, we have 2 different function machines, f and g. We want to go ahead and find the 2 reverse directions of the composition. We want to find f of g, and then we want to find g of f. And then after that, we want to go ahead and find the domain of each function and then each composite function. I'd actually like to go ahead and start here by finding the domain of these 2 functions here to start. So if I take a look at my f machine, that's just simply x squared. And so what that is, of course, is, if my writing program will allow me to write here, can I... Oh, my pen might not like this. Hold on a second. Can I write? Yep, there we go. Okay, cool. So as far as the domain of this first function, that's just f of x is equal to x squared. I'm going to go ahead and write that as script capital letter D, subscript f, just so I know what this is the domain of. And because I'm just simply squaring the input, there's not a single number out there that I'm not allowed to square. And so I'm just going to go ahead and say the domain here is just simply all real numbers, which I'll represent here by the open interval between negative infinity and positive infinity there. Okay, let's go ahead and do the domain of this function over here. So that's the square root of the input plus 5, so the domain of the function g. Now, remember that we never want to have anything under the square root that is a negative number. So typically the way that we always did this is we took whatever was underneath the square root and we said that it was not allowed to be negative. So another way to represent that would be to say that it's greater than or equal to 0, and then you would just simply solve that. X would have to be greater than or equal to 0, or sorry, greater than or equal to negative 5, I should say, okay? And so what that would look like, of course, is just going to be that interval starting at negative 5 and including it, because we can be or equal to it, all the way to positive infinity, and that is going to represent the domain of that function g, okay? So now that we have the domains of my original 2 functions, let's go ahead and actually calculate the compositions of these 2 functions. And we'll just do this really quickly because, you know, we've got a lot of practice with this here a second ago. So f of g of x, that is defined to be take f and input the output from g. And of course, the output from g looks simply like the square root of x minus 5. And what does my f machine do? That just squares whatever you gave it, and we gave it the square root of x minus 5. And you'll notice here that we've got some inverse operations about to go on. We have a square root and we have an exponent of 2. That's just simply going to leave us with x minus 5. Okay? Now, I want us to go ahead and be careful here, because if you just look at this formula for the output, you might be led to believe that the domain of this function is simply all real numbers. But we just need to be a little bit more careful about that, because in general, it may not be one of those things that it's that simple, okay? So let's just go ahead and draw ourselves a picture here, right? So I'm going to go ahead and draw a picture of my machine. So this is f composed with g, so I'm going to start with my g machine. And the idea, again, there simply was that I threw in x, the input, and I got out g of x, the output, okay? Now, we said before that the range of, or sorry, not the range, the domain of this function machine is going to actually be anything that is going to be negative 5 or greater than negative 5, okay? If you were to actually graph this function g, that is the square root of x minus 5, you would find that we would have a range of all the numbers that go from 0 all the way to positive infinity, okay? And that's important to point out here, because we're about to go ahead and give this g of x output to my f machine as the input. Okay, and the only question now becomes, is that something that we're allowed to give the f machine? Well, yes, it is, because before we said that the domain of the f machine is just simply all real numbers. It's just the machine that squares whatever you give it. And so we have the green light. We can go actually and plug this in and get the output, and that would be f of g of x. We would need to kind of think about this, because it may not be something that is allowed to be plugged into your F machine, because all we're getting out of the G machine is all the numbers between 0 and positive infinity, and it just turns out here that F machine will accept all of those, give us any errors because its domain was all real numbers, okay? And so what we're able to say there is the domain of F of G, because we have the green light there, is simply just going to be the original domain that we started with here. So just go ahead and say here the interval from -5 inclusive all the way to infinity exclusive. There we are. Okay. For the reverse direction of the composition, we're going to go ahead and do G of F of X. And by definition, of course, that's going to be G evaluated at the output of F. And of course, the output of F was X squared. Okay. And so plugging that into my G machine, I see that we get X squared minus 5. And that is going to be our function output for this function, okay? And so talking about the domain of this here really quickly, right? So script capital letter D of G of F, what would that look like? Well, again, you might have to go through a similar reasoning process there, but I will go ahead and share with you, based on that last thinking process here, that the domain here is going to be all real numbers. There's not going to be a single thing here that you're not allowed to plug in, okay? So we'll go ahead and box that up right there. All right. Decomposing functions, and so here's where we're going the other way around. So the directions say find functions f and g such that f composed with g of x is equal to h of x. Okay, so it turns out that that's what we are given is h of x, and the idea of the problem is that we have to go through and decompose this into the original functions f and g. Okay, so in order to do this, you may want to go ahead and look for, since g of x is what we plugged into f, we're going to look for g by looking for a quote-unquote inner function. And then we're going to look for f by looking for a quote-unquote outer function. Okay? So can we detect that there is some sort of inside function that is having an operation maybe performed to it? I should point out before we get started here that there are a dozen different ways that you can do a decomposition of two functions. There's a lot of different ways to look at it. So I'm going to give you a couple of sample ways, and then we'll go ahead and move on here. So as an example, I'll say example 1 here. One way that you might define g of x, the inside, and f of x, the outside, is by saying the following. Maybe you look at this as the inside function is just simply this x plus 5. Okay, so if we call g x plus 5, then that means that everything that remains there is going to be f, right? So the square root of x to the third would be my f. Okay, that's just one way to decompose these. You might look at this in another way, though. You might say, as another example, maybe instead of just simply looking at x plus 5, maybe you look at this entire thing under the square root as your inner function. So in that way, you might go ahead and define g of x as the binomial x plus 5 all raised to the power of 3, in which case f of x would simply just be equal to the square root of the input. Okay, and there are a lot of different other ways, but we just want to develop with you guys the ability to look at this and detect what that inner function is and what that outer function is. Okay, as another example here, you may look at this as by simply saying you've got this input of 5x to the third plus 6 inside. Okay, so that might be your g. Man, this writing program is really going to get on my nerves here. Come on, man. Okay. G of x right there. Okay, so we might say g of x is equal to 5x to the third plus 6 as the inside, and then as the outside, we might just simply say that that's just going to be take the input and square it, or in other words, just simply x squared. That's one way to do it. There are a dozen other ways to go ahead and do this here as well, but when you decompose functions, the idea is that can you find just an example of a way that these could decompose instead of finding all the ways, right? So I hope this video has been of some help to you. As always, if you guys have any questions, please feel free to let me know. But that's all I have for this video. Thank you very much for your attention, and I will speak to you guys in the next one.